Hi everyone, this is a video presentation of my Coursera IBM Advanced Data Science Capstone project. The project is about training machine learning models to predict if it will rain tomorrow, based on the data about today's weather conditions. It is quite an interesting topic to me, as I always open a weather forecast app in the morning to see if it will rain or not. So I think it is a good idea for me to build my own model to do the prediction. To start with, I'm going to give you a brief introduction about the dataset, the use case, and the solution. Then I'll be giving you more details about how the data are preprocessed, what and how the machine learning models are built, how the models are tuned, and how the models perform. Since this is my first data science project video, you're welcome to give me any comments and suggestions by leaving your message in the comment section below. Okay, let's get started, and I hope you will enjoy it. First of all, the dataset was downloaded from gecko.com. It is in CSV format. The compressed size is 4 MB and is 30 MB when uncompressed. The file contains 142,193 rows and 24 columns. It contains the daily weather data of different locations in Australia from 2008 December to 2017 June. As you can see in the diagram, among the 24 data columns, 22 of them are features, which our predictions are based. And among the 22 feature columns, 8 of them are categorical, and the other 14 columns are numerical. The rain tomorrow column is the label column, which contains values of either yes or no to indicate whether it rained or not in the next day of the day represented by each data row. There is a column called risk MM, which is not used because, as stated in the downloading page in gecko.com, this column is used to derive the label column, so it actually leaks the answer to the prediction model. The project is about building machine models to predict if the next day would rain with the weather information about a certain day. The model can be used for outdoor event preparation scenario, for example. Rain tomorrow column is used as the label for supervised machine learning model training. In the project, 2 non-deep learning models and a deep learning model were trained. The 2 non-deep training models are Logistic Regression and Random Forest. Feed-forward network is the deep learning model being trained. All the works were performed on the IBM Data Science platform. Apache Spark, Keras, TensorFlow, and Cloud Object Storage are the main technologies used in the project, as these are all supported by the IBM Cloud platform. Let's now go deeper about the architectural choices. Since the original dataset was downloaded externally from gecko.com in form of CSV file, and no real-time data streaming is required, CSV file is used as the data source. No enterprise data exists in this case, so the enterprise data component is not needed. Streaming analytic component is also not needed, as no real-time process of data is required in this case. Apache Spark is chosen for data integration as the source data is in CSV format, which is well structured, with which Apache Spark works best. Apache Spark also supports the widely available SQL skill set for performing the data cleansing and transformation work. IBM Cloud Object Storage is used for data repository, as the size of a dataset fits the free storage amount limitation provided by the IBM Cloud platform. The Cloud platform also provides all the necessary operating and maintenance of the Cloud Object Storage. Jupyter Notebook, Python, Matplotlib are chosen for the source data discovery and exploration as they are widely used. Python, Spark ML are chosen for non-deep machine learning, while Keras and TensorFlow are chosen for deep learning. These technologies are chosen because all of them are available on the IBM Cloud platform, and the parallel processing power provided by Apache Spark can boost the data training speed. Models produced are saved on the IBM Cloud platform. The codes and documentations are preserved in the Jupyter notebooks on the cloud platform too. IBM App ID, object storage, the IBM Cloud PaaS and SaaS are inherent technologies on the IBM Cloud environment to provide security, information governance, and system management. Before building any machine learning model, data quality has to be assessed first.
A Python script on Jupyter Notebook is used for data exploration and data quality assessment. The notebook helps visualizing the data distribution and gives statistics about data, especially on investigating missing data issue. This screen shows the output of the data exploration Jupyter Notebook about statistical analysis of two of the feature columns. This screen shows the output of data distribution of the minimum temperature column.
Data are read from the CSV file into a Spark data frame. The data frame are examined for any quality issue. The most obvious issue of this dataset is the missing of data in many columns. Besides the date, location, and ring tomorrow columns, all other columns have missing data issue. As shown in the tables, some columns have more than 40% data missing.
Some locations even have less than 5% of data availability for certain column.
As the whole dataset is concerned, less than 50% of the rows have all the data present. Many of the variable data would be lost if only the rows with all data present are used for prediction. As a result, most of the data preprocessing work is about filling in the missing data. For numerical data columns, missing fields are first filled with the monthly average of the values regarding the related location. If monthly average of a certain field regarding the related location is not available, which could happen if all the values regarding the month and the location are missing, annual average of the location is used to fill in the missing field. If annual average of a certain field regarding the related location is not available, which could happen if all the values regarding the year and the location are missing, the average of all the values regarding the location is used. If the average of a certain field regarding the related location is not available, which could happen if all the values regarding the location are missing, the average of all the values of all locations is used. For categorical data columns, fill in any missing field with an NA string and treat it as a valid category. The above operations results in all data rows can be used for prediction. Loss of any useful data is prevented effectively. The following slides show the 4 SQL scripts for creating the data views of the monthly average by location, annual averages by location, averages by location, and averages of all locations. The 5th SQL script is for creating a new data view with all numerical missing fields being filled with the calculated average values. During the filling missing data operations, numerical columns are transformed from text data type to numerical data type. Month of the year of each data row are also extracted during the process and made into a new feature. After the dataset has been cleansed, a PySpark pipeline is created to perform feature engineering. Firstly, a string indexer is used to convert all categorical columns into numerical indexes. Then, one hot encoding is applied on the indexed categorical columns. After that, all the feature columns are vectorized and made into a single features column. Finally, normalization is applied on the features column. It is now ready to build and train the machine learning models. As mentioned before, two non-deep learning models, which are Logistic Regression and Random Forest, were built. A feed-forward network deep learning model was also built. All the models use accuracy as the performance indicator. Performance of the models are then tuned and compared to see which is best in performing the prediction.
Now, let's look at the execution of the code. All the codes regarding the previous mentioned data preprocessing, feature engineering, and model building are written in Python on Jupyter notebooks. Let's now see the execution of these codes. For security reasons, some sensitive parts are blocked, and for saving some waiting time, some parts of the video has been sped up. I've put the links to the notebook in the description section for those who are interested in the Python code. Let's now execute the Jupyter Notebook for data exploration. The dataset is read from the source CSV file, and missing data analysis of each column are output in form of tables. The visualization distribution of data are output in histogram and box plot. It is found that there is serious problem of missing data in the dataset. Let's execute the Jupyter Notebook for data preprocessing now. The dataset are read from the source CSV file into a Spark data frame. Then the sequels are executed to calculate the averages, and the missing data are filled by the calculated averages. Finally, the data frame are saved into a Packet file for feature engineering. Now, let's look at the execution of Features Engineering Notebook. The notebook reads the dataset transformed by previous scripts into a data frame. Then, a pipeline is created to perform the features engineering work. Categorical columns are turned into indexes, and one hot encoding is applied to these indexed columns. Then, all the feature columns are vectorized into a single features column. Finally, the features column is normalized. Now let's look at how non-deep model trainings are done. The dataset after features engineering are read into a Spark data frame. The data frame is split into two parts, a training data frame and a test data frame. First, logistic regression models are built and trained by unnormalized features. The model is evaluated and the accuracy is 0.776, which is not bad. Testing data are used to evaluate the model, and the accuracy is 0.774, which means the model is not overfit. And other logistic regression models are built and trained by normalized features this time. It is found that the accuracy of the new model does not have any improvement compared to that of the old one, which is trained with unnormalized features. The model is then saved for future use. Random forest is another non-deep learning model being built. Again, the model is trained with unnormalized features first, and then with normalized features. There is still not much improvement by using normalized features. However, by increasing the maximum depth allowed of the trees from 5 to 25, there is a significant improvement in model accuracy, which has been increased from 0.815 to 0.964. The random forest model is then saved for future use. Last but not least, let's take a look at the execution of the deep learning model training code. As before, the dataset after features engineering is read into a Spark data frame. The data frame is split into two parts, a training data frame and a test data frame. A feed-forward network model is built, since it is either rain or not rain tomorrow. The output layer has two nodes. And after the one hot encoding, 22 features have become 143 inputs, and therefore there are 143 nodes in the input layer. Two dense layers, each has 256 nodes, and each has a dropout layer follows, are added as hidden layers. ReLU is set to be the activation functions for the dense layers, and softmax is set to be the activation function for the output layer. Stochastic gradient descent is used as the optimizer, and mean squared error is used as the loss function. The batch size is set to be 512, and the number of epochs is set to be 100. After a few tuning on number of layers, number of nodes, and number of epochs, the model has a 0.83 of accuracy. The model was then evaluated with the test data and got a very close accuracy, which indicates that the model is not overfit. To sum up, the random forest model trained with normalized data has the highest accuracy when compared with the other models. However, it is believed that there are still rooms for improvement. All the models are saved for future use.
So this is the presentation of my Coursera IBM Advanced Data Science Capstone project. I hope you have enjoyed. Thank you.